Kendal College lecture series on climate change. Now, I think you've all heard enough news about climate change in the last few years. It's one of the most challenging issues ever to face humankind. So we're going to be looking at this issue. Today, our speaker is going to be talking to us about the science of climate change. So she'll get into some of the basics around the greenhouse effect, around climate cycle, and around other issues that are central to the discussion of this as a scientific issue. Before I introduce her, though, I'd like to just say a word about another activity here on campus. This spring, an independent group of folks here on campus established a group to work on climate change. And we call ourselves the Climate Action Partners, or CAP. Those of you who are inspired after listening to Lisa today to do more, there are a couple options available to you. One is to join our CAP advocacy network if you're not already on it. And second, if you want to know more about what CAP is doing, we'll be happy to share with you information about our activities and plans. So with no further ado, I'd like to introduce you to Professor Lisa Greer, who is a professor of geology at Washington and Lee University. She's been a member of the WML faculty since 2003. She studies the decline of the coral reef in the Caribbean, including topics like the variability of the reef composition over time and sea levels increases caused by climate change. Lisa received her undergraduate degree from Colorado College in
Geology.
In geology, right? And then she got a PhD in geology and geophysics from the University of Miami. Won't you join me in welcoming to this Kendal College lecture, Lisa Greer. Lisa.
Even if they think the climate is changing or humans are causing it, don't really know much about why or how we know this. So I tried to I'm going to try and hit some of the fine points of the science and leave time for questions, of course. And you're welcome to ask questions as we go. I love studying the climate system. I'm an earth scientist, geoscientist, because I find that in terms of science, it's one of the most integrative sciences we have out there. So when I study climate change and learn about it, I'm looking at the atmosphere, the biosphere, the hydrosphere, I'm looking at ice, and all of these pieces of our Earth system are working together to drive the climate that we feel here at the Earth's surface. So it's complex, it's really quite elegant, and all of these parts are interacting to change climate over geological timescales and timescales that are more of interest to us as humans. So all of these pieces, the sun, the composition of the atmosphere, the land surface, even plate tectonics and volcanoes are all influencing climate change over time. One of the first things I hear is from a lot of people who are hesitant to believe that climate is changing or that humans are causing it, say, well, if you look at geologic time, the climate has always changed. You know, back when the dinosaurs were around, seas were flooding the continents and it was much, much hotter than it is today, and that's absolutely true. There are numerous reasons why the climate changes, and for us as humans living in the Earth system, it's really how it changes now, why it changes, and how much that matter to us as humans. Because the Earth system has seen a lot of changes, but what's happening now really impacts us, and you'll hear about that in some of the later talks, I think, in the series. So this graph is of 4 of the last ice ages. And what you're looking at here is temperature that is derived from ice core data. And so what we have over on this side is 400,000 years ago, moving towards the present today. And we see these beautiful cycles. We call it a sawtooth pattern, like the blades of a saw, and it goes warm and then bumps down to cold. Warm and bumps down to cold. And we see this pattern. I could go farther. I could go another 4 ice ages back, and we'd see that same sort of pattern. And so we see this in ice core records. We see it in sediment records from the ocean. We see it in lots of different geological materials, this pattern emerging. And again, we might say, well, in the Cretaceous, when the dinosaurs were around, it was much, much hotter. But these are the time scales of interest to us as humans. I've placed here the evolution of modern humans, 200,000 years ago, and just for fun, because Neanderthals are interesting, the extinction of Neanderthals, let's say 40,000 years ago. So this is just to look at our time scale of interest to us right now. So then we want to think, how much of a change is it from the last ice age, about 18 to 20,000 years ago, up to present day? Like, what does that mean? How big of a change is that? Because it's not the magnitude of the dinosaurs to us. And it turns out that that's a big change. So 18,000 years ago, it's a little hard to see this, 18,000 years ago, this was all covered in ice. In fact, my husband, his family's from Canada, and I like to joke that Canada was covered. Nobody was living in Canada back then. As a matter of fact, it was like 3 to 4 kilometers thick of ice just 18,000 years ago on, northern North America. So for us as humans, we couldn't live there. It changed our migration patterns. It changed a lot about where we could be and where we went, and dictated a lot of where we ended up going. As opposed to today, where we now have moments of ice-free Arctic Ocean, right? So I'm not saying this is all due to humans, right? I'm just trying to give you a sense of how big that change over 18,000 years can be, right? So my training is in proxy records of climate. So we don't have thermometers or historical records from when the Neanderthals were around. So how do we actually know that it was colder and how climate has changed? And we can look as earth scientists at geological materials. And we look at the chemistry of those materials, how fast they accumulate, and we can translate that into past temperatures. And an example of this that most people are familiar with is tree rings. So trees grow annually, and they have these beautiful annual records, and we can count back when a tree is cut down and figure out how old it is. As a scientist, a dendrochronologist who studies tree rings and climate, what they can do is they can look at the thickness and how it varies from year to year. That might tell them something about precipitation. Or they can look at the composition of that woody material, and it might have something to do with atmospheric composition. Now, we don't cut down trees anymore as dendrochronologists. That would be just rude. We like our trees, so what we do, and we can do this on the WNL campus, is we take little cores. We drive little cores into trees, pop them out, look at them under a microscope, sample them for their chemistry, and learn something about the environment even here in Virginia. What I do is I study corals. And so what we do is we actually drill down through living corals, and they have rings, just like trees. And I can look at the chemistry of the coral skeleton through time, and it tells me something about the temperature of the water, the light, for instance, how cloudy it was. And it's really pretty remarkable. This is one of my students, after we've pulled out a core from a coral. The coral's only living in the outer millimeter, and we have a way of sealing it up so that it grows back over that hole. And then sometimes, this is probably my favorite picture of myself because I spent so much time upside down. I dug a pit that was about 2 meters deep in a dead part of the reef and sampled the corals all the way down and showed that that coral had been living there for a couple hundred years without any breaks in the record. This is in Belize. So we can do a lot with these materials that we have to work with. This is another site, and 2 of my students, we took a ropes course and went to the Dominican Republic, and we sampled every 5 centimeters up that outcrop, and all those are not rocks, they're dead corals that lived from 8,500 years ago to 7,300 years ago. And so we can look at the chemistry, and we can tell what temperature the water was that they grew in. And the way we do that, by the way, is we grow, my colleagues that are biologists will grow these corals in tanks, change the temperature, and then sample the skeleton and see what that relationship is. So it's experimentally derived. So these are the kinds of ways we can get at reconstructing past climate. And some of our best records from the ice ages are from ice cores. And I was very fortunate. I taught for 2 years at Penn State before coming here. And I worked with the guy with ice in his beard over there. And they've drilled 2 miles down in Greenland and extracted cores with annual records. And you can see what they've done. Here's the drill bit and the drill rig. And then they slice them in half and put them on light tables. And you can even sort of see these years barely. And they can count back, and they can do all kinds of neat things with the ice. Little syringes to suck out bubbles of gas, and they can measure CO2 and how that's changed every year down like 800,000 years in some cases. They can melt the ice in small increments, and they can see how much sodium chloride is in there, and they know how much sea spray. They can measure, extract the dust from these ice cores and fingerprint it, as a good geologist can do, and tell which way the wind was blowing. They can, because they can tell, wow, that dust matches this outcrop in China, and this one matches somewhere else. The wind's shifted. So there's so many different ways these clever scientists have figured out how we can reconstruct climate. Now, what are the main stories we get? Well, this is the top half of this graph is now revealed, and it shows carbon dioxide from the same core. So while one scientist is sampling the water for the chemistry and the paleo temperature, the other is sucking little bubbles of air out and measuring CO2. And what we see here is a really strong, statistically very strong, positive relationship between carbon dioxide and temperature. Now that doesn't, correlation is not causation, right? They vary, they co-vary in the same way. So if we're going to believe that one is, influencing the other, we have to understand what those mechanisms are, right? So we see these beautiful patterns, and scientists ask, what is causing those patterns? And so often when I hear, well, it's the sun that's driving climate, humans don't have anything to do with it. Well, through the ice ages, the sun was driving the pattern of the ice ages. I'm sure most of you know that we don't circle around the sun in a circle, rather. We have an elliptical orbit. We swing wide and we come close. Our axis is tilted. Sometimes it's tilted more, and sometimes it's tilted less towards the sun. Our axis even wobbles. So these things are very quantifiable. They create patterns in where the sun is felt with respect to us on the Earth. And that changes climate. So through the ice ages, the sun was really driving the pattern that we see in that past graph. But what's really, really interesting here is that scientists all over have tried to recreate that magnitude of temperature change in the ice ages with the sun, and they can't do it. The pattern matches beautifully. But that magnitude of change that created or melted all that ice, it can't happen. Nobody has even claimed to be able to melt all that ice with just the sun. And so what we know now is that there are feedbacks in the system. There are things that amplify that signal from the sun in the ice ages. One of the most prominent is carbon dioxide, the greenhouse effect. So the greenhouse effect is simply that there are particles in the atmosphere that trap heat. And the way I explain it to my students, it's not perfect. Those of you who know a little physics are probably saying, oh, come on, you can do better. But the sun emits shortwave radiation, and it can wiggle past these particles pretty well. It makes its way down to our Earth and heats us up. When it comes down to Earth, it converts to a different form of radiation, which is long-wave radiation, and that bounces back out. So we're all emitting heat. Me more than you probably, because I'm excited and nervous and up here talking. But I'm emitting heat back out to space. This carpet is. Anything above absolute zero is emitting energy back to space as long-wave radiation. But that long-wave radiation can't wiggle past some particles as well. So it can't pass through or past water vapor or carbon dioxide as effectively as it got in. And so we have some heat that's trapped on the Earth. And that's good. If we didn't, we'd be popsicles because it would all bounce back out to space. So it's a good thing we have something to trap some of that heat. All right, so that amplifies the signal from the sun in the ice ages. So the first thing we want to, I tell my students to try and remember is that the sun creates the pattern of the ice ages. It's a pretty beautiful pattern, and it's pretty predictable, and it's the same for the last 8 ice ages. Now the next thing that I try and get across to the students is the importance of carbon in the system. Because if we're worried about carbon dioxide, let's try and understand where it's coming from, where it sits, and all of that. And so these numbers reflect how much carbon we have in different reservoirs on the Earth at any given time. So carbon is fixed on the Earth. We don't have much carbon, if any, escape out to space. It's negligible. Occasionally a meteorite will come to Earth and bring us a little new carbon, but it's very, very small. But that carbon can move around the system and redistribute. But at any given time, what we see is that we have maybe 600 gigatons in the atmosphere sitting as gas, CO2 or methane. Organic, it's about the same amount, so that's in our vegetation and on our bodies and the soil. But what you see here is that most of the carbon, by orders of magnitude, is sitting under our feet, right? In rock and sediment. So most of the carbon at any given time is sitting under our feet. So people say, well, why worry about this little tiny bit in the atmosphere compared to all the carbon on Earth? It turns out that it's pretty important because of what it does in the atmosphere. Now, if there's one takeaway that I ask my students to think about, we've all probably heard the term fossil fuels, right? So fossil fuels are rock and sediment. It's the oil and gas and coal underneath our feet. That's the purview of geologists, okay? And what we do is we dig that up, and then we combust it here at the Earth's surface. Now, if we look at a natural system before humans, through the ice ages, and we think how this carbon travels around the Earth's system, what we see is that it travels pretty easily from the atmosphere down to vegetation. That's photosynthesis. Plants are sucking in that CO2 and transferring it from the atmosphere to the organic matter. All right, and then they die, decompose, and they transfer it to the soil. But then when the soil, actually the microbes in the soil process it, they send that CO2 gas back out. But where is the slowest exchange? That's happening pretty fast. But see, these are 50, 100, 50, 0.2. So in a natural system, carbon moves very slowly from rock and sediment out to the air. And the way it does it is by volcanoes, right? And so a lot of people say to me, well, we don't, any carbon dioxide that's accumulating in the atmosphere. My dad actually said this, just a couple months ago. He sent me an article and said, no, I read that one volcano that just erupted is more than all the cars we've driven in the last year. So I said, Dad, I'll look that up for you. And volcanoes normally move carbon very slowly, right? There have been times in the geologic past, I love the deep, deep Earth history, where they've been more active and moved carbon faster. But not now. So at present, volcanoes emit about 130 to 380 million metric tons of carbon dioxide per year. That's a lot. And that's what my dad was reading about. He's reading about all those million metric tons of carbon that are moving up through volcanoes. However, humans emit about 30 billion tons of carbon dioxide per year, which is 100 to 300 times more than volcanoes, by burning fossil fuels. So in fact, the math and the data show us that we are swamping that volcanic signal. And the volcanoes are still blowing, right? So what we're doing is we're accelerating that movement of carbon up to the atmosphere really fast. So that's the crux of the fossil fuel problem. Let's say we can pretend that it doesn't have anything to do with ethics or economics or money or any of this. As a scientist, what I see is a grand experiment that hasn't been done before. There was nobody to dig up and burn that before and move it and accelerate that motion to the atmosphere. So that's what's happening right now, is we're just speeding it all up. And I'll tell you about the IPCC in a minute. Some of you may know about this, but in their latest report, they show that, all right, let's take this argument that what we're seeing in the climate system and global warming, let's say that that's natural, right? And so what they do is they run lots of different simulations and models to show, okay, let's put in what we know of the sun. Let's put in what we know of how much volcanoes are moving carbon. And let's see what temperature should be. And so what they show here, it doesn't show up very well on this graph, is here is the natural only solar and volcanic contribution to temperature, okay, from 1850 to 2020. So if we took out human fossil fuel use, this is where we should be. But this is the observed in dark and the simulated human plus natural signal up here. So what we can see is the models show, this is degrees Celsius heating. The models show us very clearly that if we just use the sun and the volcanoes, it doesn't replicate what we observe in the in our records since the Industrial Revolution. So these are just data using models to try and understand the contributions of various components. So another thing that I often hear is that global warming stopped. And in fact, I hear this in politics. You'll hear it in the news and things like that. And a big narrative that some of you may have heard was that global warming stopped in 1998. In fact, that's something that I continue to hear today, that global warming stopped in 1998. And there's a reason behind this. There's a very well-known and famous person who said this. And the reason was, in 1998, so that's about here, okay, it was really, really hot. It was an El Nino year. It was a really, really hot year. And El Nino is a natural phenomenon. And the next year, in 1999, it was cooler. And so you can see, this is where global warming stopped. Okay? And so, I guess it stopped here too. And here, and here, and over this time period. So if you're not careful, and you don't look at all the data, you can make up all kinds of stories, right? And so let me show you what the data show us today. So these are real global average temperatures measured from 1880 to 2019. And what they've done here in this graph, it's an anomaly graph. Basically, this is a very common way of looking at data. We take the average temperature for all those years and subtract it from each year. And that gives us this baseline. So this is average temperatures for this whole period. And there's just no denying what the data are showing us, that it's getting warmer. It's getting warmer through the years. It's not due to the sun. It's not due to volcanoes. And it's a pretty clear trend. So when I hear that global warming stopped in 1998, I don't know what to say, except it didn't, right? Yeah, and it bumps up and down. There's natural variability. There are El Ninos. There are other climate phenomena that are imprinted upon this large scale. You know, I'm going to see if this works. No, it won't. That's okay. I can provide this link for you, and it's a really beautiful, just a YouTube video that simulates and shows you how climate has changed over this time period because we're not just looking at global averages, we're looking at how it impacts every place on the earth. Okay, it doesn't heat up all at the same rate at the same moment. So you can see here, for example, that's 1890 to 1894 averaged together. And here's 2013 to 17 averaged together. And you can see they look very different. So it's not just number counting. It's not just that the world is getting warmer. It's that all of the places in the world are feeling this change. We can do the same sort of thing for precipitation, and that's changing dramatically as well. And I often hear, well, wait a minute, it's not global warming, right? Because this is blue, which means cooler. Well, it is global climate change. On average, the world is warming. But there are pulses, and we feel it differently in different places that we stand on the earth. And so that's an important point. And you can see that up at north is feeling that heat a lot more than some other places. Okay. Have any of you heard about the new IPCC report? This was sort of news. Okay, this is one of the biggest international scientific ventures in history, if not the. And it's scientists from all over the world that get together and have for many years to try and keep track of the state of the science. That's the first thing. And then adaptation and mitigation strategies. What do we do about it? So those are the other reports that come out. And they just released the most recent 2021 science, basis for the science here. And it was pretty interesting because some people might criticize this or have in the past said, oh, these alarmist, crazy climate scientists, they're just exaggerating. In fact, as a scientist, looking at what they say, they've been a pretty conservative group because this group of scientists doesn't want to get it wrong. So if anything, in the past, they've underestimated the impacts of climate change because they don't want to say something that's wrong. Okay? They don't want people to discredit the science, so they're very, very, very careful. And it's been really interesting to see the results of their report. And what they show, which we already knew, we've already seen this, is that if we were to follow our relationship with the sun, we should have been cooling. All data suggests that we should have been cooling for the last 7,000 years. We were at a peak, we should have started to move down. No worries, it takes 90,000 years to get to an ice age. I won't be around then, but we were on our way down, and all the data across the world, and tree rings, and ice cores, and coral records, and sediment records back this up and show that, in fact, if we average them all together, the world was getting cooler until the Industrial Revolution, and it went like this. So, again, the data are very, very clear with respect to this. We know where we should be in the Ice Age cycle. We should start cooling. We were cooling. And then we started warming again. So that's 2,000 years there. And we see that the Industrial Revolution has had a mark. These are just some talking points. What they do is they have the headline statements in the summary for policymakers. There's a lot of, I would encourage you to look online for AR6 because they've got some really nice visuals, they've got summary reports, and then they've got the whole big thing, which is a beast. It's really, really big. And what really struck me and has been all over the news is some of the wording they've used this time around. And they say it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Now, that's a really strong word for scientists to use. Scientists hedge their bets, right? They ascribe error bars and uncertainty. And we try and be very honest about what we don't know. So unequivocal is very striking. The scale of recent changes across the climate system are unprecedented over many centuries to many thousands of years. Again, those are really strong words for a scientist. We tend to shy away from phrases like that. You know, the other concern is that carbon sits in the atmosphere as a long residence time, about 500 years. And so another worry we have is that we can't just stop putting it up there. What's up there is going to stay there and continue to warm the planet for a while. So they're saying that temperature will continue to increase, all right, under all possible emissions, whether we stop today, slow today, you know, under all these scenarios. And they also point out that whether or not we warm by 2,100 to 1.5 degrees Celsius above average or 2.0, that matters. If we're not careful, we're going to warm even faster than that. And when we see warming that's faster than that, it becomes a really big problem. So these are just some of the many takeaways. So I wanted to mention natural disasters because we've seen Ida, we've heard about storms, and one of the things I hear, well, you can't say that any one storm is due to climate change, right? Has anyone heard that? You can't. I mean, and it seems like a fair statement, right? It seems like a fair statement. So I really like this analogy, okay, in answer to this relationship. Let's see, okay, so this is the idea. If a baseball player is on steroids and has a 20% better chance of hitting a home run because they're on steroids, you cannot attribute any one of those single home runs to the steroids, right? It could be the wind speed, it could be a good eye, right? But that baseball player still has a 20% better chance of hitting it out of the park. And that's such a good analogy for what we're seeing. what happens is when the oceans are warmer, that's fuel for hurricanes. Hurricanes feed off of warm sea surface temperatures, right? So we can't say that little disturbance off the coast of Africa is because of climate change, but we can say that it's got a 20% better chance of becoming a larger storm because of the fuel that it's taking in from the ocean. Now, this is just a dramatization, like this is that arrow over here is the I don't know, right? And so we don't know. We're running an experiment, and we don't know how far CO2 is going to get up there. What we do know that's interesting, though, is that these are data, and they go back another 4 ice age cycles to 800,000. And at the peak of the warm periods, it's always topped off, 300 parts per million or lower. Okay, so this is as high as it's gotten for the last few ice ages. That's carbon dioxide. Oh, listen to that. And so, does anybody know where we're at today?
450.
Yeah, well, we're inching up there. This is where we are today. As of January, okay, this is a real number. So we've doubled the carbon dioxide in our atmosphere from the peaks of these last warm periods. Doubled it. So again, you can take all of the ethics and economics and set it aside for a moment and just recognize that what we're doing is we're running an experiment that hasn't been run before. So our system is changed in a meaningful way. And that carbon dioxide traps heat. There's no doubt about that. We've known that for hundreds of years. So that's a problem. Now, the last thing I want to mention is what's next. Because this is an area of focus I've entered in with my students and really enjoyed thinking about. As a scientist, I know how dire this situation is. So I see the frustration and the despair even in some people today thinking about what's next. I've got kids. My kid just went to college. I'd like to think that they are going to have a place that they can enjoy with their own kids, right? And so I've tried to start thinking about what we do with it because there are lots of really brilliant minds working on this. And the idea that we can just slow down fossil fuel use and stop driving cars and that's going to fix it, it's not realistic. Nothing supports that as the only answer. I believe that we're going to have to find ways to take the carbon dioxide out of the atmosphere. It's called geoengineering. There are other really crazy ideas. I won't even go there, like mirrors in space and things like that. But some really viable ideas come from geology. And if you look in the news, I encourage you to look up the company CarbFix. It's in Iceland, and Climeworks. And what they've done is, they've essentially created artificial trees that suck carbon dioxide out, like photosynthesis. And what they do is it's so neat, they take that carbon dioxide, dissolve it in water, making fizzy water. I mean, that's what you're doing when you're drinking a carbonated beverage. It's carbon dioxide in liquid. And so they make fizzy water from the carbon dioxide they're taking out of the atmosphere. And then they pump it down into the bedrock. And it turns out that the bedrock there has a lot of calcium in it. And that carbonated water combines with the calcium and it makes limestone. It's so nifty. It's limestone, just like the limestone that this place is built on. Right under our feet. This is the Edinburgh limestone. Same composition. So what they do is they literally bubble it down through the rock and it makes these crystals of carbonate. So it's taking it and sequestering it, taking it out of contact with the atmosphere. This is a porous rock with bubbles in it, and it's filled up with carbonate from that fizzy water from the atmosphere. The other thing they're doing is they're pumping it into greenhouses. And they're using it to create super tomatoes and pickles and things like that. Well, cucumbers. So there's no going back from some of the changes. They're inevitable. We've set some things in motion. However, and this is the key point, we still, and I am an optimist, we still have the ability and a brief moment in time to do something about it, to mitigate, to slow it down. Rather than a 2.0, let's go for a 1.5 degree warming, right? And the best case for that is this last slide that I'll show you. These are models created by these scientists for the IPCC. And these are based on human behavior. So this model says, all right, by the year 2050, we've become carbon neutral. We've figured out how to do it. Washington Lee has a carbon neutrality goal of 2050. All right, for example. All right, and here's one with some other scenarios that we can use. Here's if we let it run amok, and we just don't care, and we keep pumping it up into the atmosphere. All right, here is, all right, we're sort of getting it together, but not quite. Well, the difference here, this is in gigatons of carbon we put up in the atmosphere per year, makes a difference. Because these are the outcomes of these. We've got 1.5 degree warming if we follow this path. This is based on our behavior and our choices. If we go this route and let all the carbon up into the atmosphere without sucking it out, we're talking about 5 degrees Celsius warming. That's more than devastating. Now that's an end member. I'm not saying that this is what's going to happen. I think we're smarter than that. But this is what the science shows us, right? So I believe in taking carbon dioxide out of the air and making rocks. It'll give my students plenty of jobs in the future too, which is nice. So yeah, that's all I have. I don't know if there are any questions.
Thank you very much. You've offered us some very provocative thoughts, Lisa, and I want to ask if there's anybody in the audience that have questions about. Hardly.
Lisa,
Yes.
how much can science do if government doesn't do anything?
I think that's one of the key problems. What can science do if the governments aren't doing something? Fair enough. I think that this problem is very much like many of the other problems that we've solved that government was involved in. For example, a lot of industries used to say that smoking doesn't cause cancer. And so that was an unregulated industry. And eventually it became apparent that there was no denying it, and regulations had to be put in place. It's the same with the ozone layer. People said, no, we still want to make our hair spurties and things like that, and it's not a problem. But the science, the data finally amassed, and people had to do something about it, so they changed their use of refrigerants. It's kind of a matter of how fast we do it, and the governments need to listen to the scientists. I'm biased, yes, because I'm a scientist, but I spend a lot of time looking at the data with a critical eye, and I just think that eventually people will come around. I think people are coming around. People need to vote for scientists. And I'll just go right out there and say, there are plenty of Republican coalitions, that people who believe in scientists. Vote for those people then. Vote for the Democrats that believe in science. Vote for the Republicans that believe in science, and I think we'll get somewhere. I wish it was faster. Does that sort of make sense? Yeah.
Next question, Karen.
How far along is this science that takes the CO2 out of the air and turns it into limestone? I mean, is it, I'm assuming it will take a lot of money to do it all. I'm just really done with that. But why don't we hear about it? I mean, I do hear things just referred to a little bit here and there, but not taken real seriously.
Yeah, so this is where it gets exciting. The technology has been pretty robust, but the problem is that people haven't been able to figure out how to scale it up at cost, right? But right now, there are, most of the major oil companies, for example, have had in their long-term planning, I'm a geologist and I work with a lot of oil and gas people, have had for years in their long-term planning a carbon tax. They've been planning for it, right? They've been planning for carbon offset programs. They're poised and ready to go. They're smart, really smart people. And so what's going to happen, what's already starting to happen is that people are going to be buying into carbon fix and Climeworks to offset their emissions. And it's already starting to happen. So it was just last week that they had a new plant come online. The technology's there, the capability's there. It's the money in trying to figure out that cost-benefit analysis. However, I really think like Walmart and a lot of these companies know and recognize, and their boards recognize that they're going to have to start paying for their pollution. And this is the way they're going to do it. So they're going to fund this. Now, it's not a publicly traded company yet, because I'd love to get in on it. They're going to soar.
What's the name again?
Climeworks and Carbfix, and I'm watching them.
You have that written down somewhere?
And I'll give you another little hot tip. KRBN, Carbon is a fund that is banking on the price of carbon going up, meaning people are going to have to start paying for it. And I've watched their stock, I invested a little. It's the consistent, no matter what the market's doing, carbon is going up and making money. So it was a safe bet. I really feel like it's as safe a bet as I'd ever make. Yeah.
In a capitalist society, you always have to respond to capital markets, right?
Yeah.
Back here.
How much do you think trees and plants and regenerative agriculture are adding to that sequestering?
Yeah, that's a great question. This is something that people are now recognizing more and more as a very important piece of the puzzle, the way we use our land. I will say, though, that it's not enough to cover everything, but I'm going to be clear that there's no silver bullet here. Carbfix and Climeworks, they can suck carbon out, but we're still also going to have to reduce our use. We're still also going to have to invest in regenerative agriculture. It's just a multifaceted, wicked problem that we're going to have to tackle from all sides. And regenerative agriculture is a really important piece of that. However, we used to think that go plant a tree and save the environment, and it's not enough. It's just not enough right now. But if you look at it, there are places where wind makes sense. Texas. Texas is the leading, is the leader in wind technology, renewables, wind renewables. In Arizona, it's solar cells, right? Solar is a really big, important piece of this. There are other places where regenerative agriculture is critical, is key. Where there's hydropower, or geothermal, or direct air capture. So it's really going to take that kind of thing, which actually makes it more easy to envision. If we don't have to put all our money into one thing, then I can see this actually a more accessible problem to tackle.
I have a question back here.
What does regenerative agriculture actually mean?
That's an excellent question. And my friend and colleague David Harbour, if any of you know him, he's the expert in this. It's the idea that the way we manage our soil actually puts carbon back into the soil. So for instance, when we till up our crops, and I've been tilling my garden for years, we're actually losing a lot of that carbon, and it's decaying and moving back up to the atmosphere. But burying that carbon regenerates the soil, gives much higher soil fertility, and it also sinks that carbon in the soil rather than exposing it to the air.
How do you bury it?
Well, one is that you don't unbury it. You don't expose all those yummy microbes and that fresh dirt to the atmosphere. You have it layered down in there and protected underneath the soil, underneath the surface. But I'm not an expert in this. I wish I was.
That's good.
Last,
Lisa, there are other gases besides CO2 that contribute to the global warming. What percentage do they contribute compared to CO2?
That's an excellent question, and one that I'm actually really interested in learning a lot more about. But for instance, methane. There's a lot less methane in the air than there is carbon dioxide by volume, but it's really effective at trapping heat. It's really, really effective. And one place we see this and we really worry about it is in the Arctic tundra. So we have soil that has a lot of methane in it, and the ice is essentially keeping it trapped in the soil. And when that ice melts, it releases methane gas. We even see it in oceans, this happening, heating up and releasing these methane, what they call as methane burps, up into the atmosphere. Those are very worrisome and haven't been factored into a lot of the models we still have a lot to learn about the contribution of methane. But it is fairly scary because a little bit of it goes a long way. And that's also rice paddies and cows and things like that.
Lisa, how about the retention time for carbon versus methane in the atmosphere?
So carbon, whether it's in methane form or carbon dioxide, has about a 500-year residence time. And so that's the thing is, look, the idea of sucking carbon out of the atmosphere has been a very scary one. And some of the greenest people I know don't want to think about it because it's not natural, right? It's not natural to try and think about artificial trees sucking it out. And then who controls it, right? Who gets to decide how much carbon we take out? Those are really thorny ethical issues and things like that. I just think that we've reached a time where we don't have much choice but to think about that because what's up there is going to stay for a while.
Ed, you have a question?
You mentioned the tundra and the methane, and maybe this is a point to be depressing and talk about what they talk about tipping points. What does that really mean here? To me, it means things get a lot scarier really fast.
Yeah. The biggest tipping point, the one I get most nervous about as a geologist, is that the faster we melt ice in the North Atlantic, like Greenland, the faster we melt that ice, the more it dilutes the saltiness of the water in the North Atlantic. And the only reason our oceans are churning around the world and bringing warm air up to Europe and bringing cold air down to the tropics is because of the churning of this conveyor of heat. And one thing we've seen in the geologic past is when the oceans stagnate and stop moving, pardon me, but all heck then breaks loose, right? And we have seen massive scale changes in climate systems, even during the time of humans, like 11,000 years ago. Now, we worry that there's a tipping point that may come if that ice melts too fast and shuts down that conveyor. Then we're really in trouble, right? It's sort of a low likelihood, massive impact scenario. And as far as tipping points are, I deal with college students, and I also have kids, and that does inform a little bit of how I process some of the science. Those tipping points are there. Our job is to do everything we can to avoid them. That's where we're at, because we don't have a choice but to try and avoid those catastrophic scenarios, right?
We have time for a couple more. Robin in the back.
Back to the carbon capture, have scientists thought of any of the unintended consequences
Yes.
of creating all that limestone or whatever other
Yeah.
theories they have?
And that's something, I have a bank of literature that I give my students that's several hundred scientific papers about this topic, and it's up to them to sort of sort through some of it. Yes, this is one of the reasons why people have slowed the progress in this area, and why some of these technologies haven't developed as fast as they could, is because there are unknowns. But I would argue that there are so many unknowns that we're facing right now that we can't afford to ignore the possible side effects of sucking the carbon out. Now, I do not see any negatives to making limestone. Limestone is essentially the same thing that you chew up in a Tums tablet to neutralize acid in your stomach. I mean, so I don't see a problem with that particular one, but there have been proposals to spray aerosols up into the atmosphere cooling that mimic the cooling effects of volcanoes. Sulfur dioxide. Those are things that people have said they're too risky, we can't follow that path. So there are people still exploring some of this, but not in very, they're not going to come online. So I think that this one, that's why I like this particular idea, is that when people look at it, no one's really finding any negative impacts that are catastrophic or something like that. But yes, it's a very real problem, and one of the reasons why it hasn't been funded and we haven't pursued some of these things aggressively. Yeah.
I'm looking outside.
Bill? Just like to compliment you on the way that you handled this. You laid this out in a way, the basic science, in a way that we have seldom seen or read, or even heard about. You put it all together.
Well,
Thank you
thank
very
you.
much.
That's so nice of you to say. I mean, I think that goes to the heart of one of the biggest problems we have with dealing with this, is that, unfortunately, it's hard to communicate this stuff sometimes. And it's hard to sift through all the news. It's especially challenging right now, I think, because we have politics and economics and science all mixed together in this big jumble. And I look at it as science first and see where that takes me.
You're working with a generation that will probably solve these problems, or at least dead them a little bit.
I'm hoping.
Bill?
Yeah, quick question. If the North Atlantic circulation were interrupted, the failure to bring heat up into the north, wouldn't that cause a small ice age up there or something, or is that just temporary?
Well, that is what we think happened with the Little Ice Age.
Exactly.
Exactly. So we think that slowed down, that circulation slowed down, and there was ice on the River Thames because of it, right? The question is timescale. So for humans, what we saw, like the medieval warm period, was nice and lovely and wild crops and just a lovely time to get food from the natural environment. And then we slipped into the Little Ice Age. And, people can handle it for a year or two. But then they don't have the drying barns and the storage, and what we see is collapse. It doesn't take long for us as humans in history to get upset and angry when we're hungry. And that's caused wars in the past. And I think that's one of the things that we're very concerned about. If that circulation stops, it changes agriculture worldwide. And that changes food and our availability, and that causes unrest, civil and social unrest. When people can't get food, we're seeing it today. In communities where people can't grow food, there's a lot of unrest.
Right. Thank you very much, Lisa. This is
Thank you
great.
all.